Hi class. So this is the second half of the factors that can affect relative humidity. So previously we looked at the influence of adding or removing water vapor from the air, and I gave you an example of adding water vapor to the air. Okay, and again, if we take a look at the relative humidity equation, just from a math standpoint, you can influence the relative humidity by either influencing the numerator or the denominator. Okay, in this particular case, we're going to influence the denominator. Okay, we're going to change the saturation mixing ratio. So remember, the saturation mixing ratio is dependent on the air temperature. Okay, if you know the air temperature, you know the saturation mixing ratio. Okay, and so what we're going to do is we are going to change the temperature. Okay, so a second factor that affects relative humidity is changing the air temperature. Alrighty. And so we're going to do another example, very similar to the previous problem, previous example, I should say. And so we'll start off with temperature. Okay, and then we'll take a look at the mixing ratio. Okay, if we know the temperature, we know the saturation mixing ratio. So we'll put that in our table here, and then we'll calculate the relative humidity after we've changed the air temperature, which will change the saturation mixing ratio. Okay, so let's start off our example here with a temperature of 20 degrees Celsius. Okay, and now what we're going to do, so last time we kept the temperature constant, and therefore the saturation mixing ratio stayed constant. This example, we're going to change the temperature. We're going to decrease it, and therefore we're going to change or decrease the saturation mixing ratio. But the actual amount of water vapor in the air, let's hold that constant at 7 grams of water vapor per kilogram of air. Okay? So with a temperature of 20 degrees C, if we take a look at the saturation mixing ratio table, if our temperature is 20 degrees C, our saturation mixing ratio is 14 grams per kilogram. In other words, at a temperature of 20 degrees C, the air can hold a maximum of 14 grams of water vapor per kilogram of air. Okay? So our saturation mixing ratio is 14 grams per kilogram, and therefore our relative humidity is 7 grams per kilogram, the mixing ratio, divided by the saturation mixing ratio, 14 grams per kilogram, so this comes out to 0.50, okay, or 50%. Okay. All right, now what we're going to do is we're going to decrease the temperature of the air by 5 degrees Celsius. Okay. So we're going to decrease this to 15 degrees C. We are going to hold our mixing ratio the same, the amount of water vapor in the air. We're going to hold that constant at 7 grams per kilogram. Okay, our temperature decreased. As air gets colder, it can hold less water vapor. And so if we go to our saturation mixing ratio table, at 15 degrees C, the maximum amount of water vapor the air can hold is 10 grams of water vapor per kilogram of air. Okay, so underneath saturation mixing ratio, it's 10 grams per kilogram. And now in this particular case, our relative humidity will be our mixing ratio, 7 grams of water vapor per kilogram of air divided by the saturation mixing ratio, 10 grams of water vapor per kilogram of air. And so this will give us a decimal of 0.70, okay, or the equivalent of relative humidity being 70%. Okay. So all is well and good. I hope you're following along. Just just fine now. Okay, let's decrease the temperature of the air by another 5 degrees Celsius. Okay, so our air temperature falls to 10 degrees C. We're going to, again, hold constant the amount of water vapor actually in the air. Okay, 7 grams per kilogram. Okay, air temperature is decreasing, so our saturation mixing ratio should be decreasing. With a temperature of 10 degrees C, the air can hold a maximum of 7 grams of water vapor per kilogram of air. Okay, and so 7 grams per kilogram is our saturation mixing ratio. Therefore, our relative humidity is 7 grams, the mixing ratio, 7 grams per kilogram, divided by the saturation mixing ratio, 7 grams per kilogram. This comes out to 1.00 or 100%. So we are saturated. Okay. But let's not stop there. Let's decrease the temperature again. Let's decrease the temperature by another 5 degrees C, down to 5 degrees C. And if we hold our mixing ratio constant, 7 grams per kilogram, okay, at 5 degrees C, okay, if we decrease the temperature of the air down to 5 degrees C, our saturation mixing ratio decreases. Okay, the warmer the air is, the more water vapor it can hold. The colder the air is, the less water vapor it can hold. At 5 degrees C, the air can hold a maximum of 5 grams of water vapor per kilogram of air. Okay, and so therefore our relative humidity will be the mixing ratio, 7 grams per kilogram divided by the saturation mixing ratio, 5 grams per kilogram. This comes out to 1.40 or 140%. Okay. If you remember from the previous video, though, relative humidity in nature cannot be above 100%. So our relative humidity cannot be greater than 100%. Okay. So what happens then is the relative humidity equals 100%. Okay, so we had 7 grams per kilogram of water vapor in the air, but it could only hold 5 grams of water vapor per kilogram of air. So our relative humidity is 100%, and this extra 2 grams of water vapor, so 2 grams per kilogram, condenses. And in nature, that's going to condense once again into dew or into cloud droplets if it's up in the atmosphere. So if it's at the surface, it's going to condense into dew. If it is up in the atmosphere, it will condense into cloud droplets and you form a cloud. Okay? So those are the 2 ways that you can affect relative humidity. Add water vapor or remove water vapor from the air. That influences the numerator. Or you can change the air temperature, increase or decrease the air temperature. Okay? And that will influence relative humidity. In this particular example, we decreased the air temperature, which increased the relative humidity. Okay? But if we started off at 5 degrees C and worked our way up, if we increased the air temperature, then our relative humidity would decrease. Okay? All right. So if you have questions, make sure you let me know.